Today I'll talk about Crank-Nicholson method for parabolic PDE. Here is the general form of the heat equation. Dou U by dou T is equal to alpha dou square U by dou x square, where uxt is equal to unknown function. It can be temperature, it can be concentration, or etc. Alpha is here diffusion coefficient, and the equation describes the diffusion process. So here is the objective. Derive the Crank-Nicholson method as an accurate and stable numerical scheme. Now first we have to use finite difference approximation. So first discretize dou U by dou T. Dou U by dou T we can write uin plus 1 minus uin, where uni solution at position xi and time tn. Now we can discretize dou square U by dou x square. So that is ui plus 1 minus 2 ui plus ui minus 1 del x square. So here it will be n, it will be n, and it will be n. So here del x spatial step size, del t time step size. So based on that we can put in that before that here explicit and implicit method. So here we know that the heat equation is dou U by dou T is equal to alpha dou square U by dou x square. So implicit, if we use implicit method, we can write uin plus 1 minus uin del T is equal to alpha ui plus 1n minus 2 uin plus uin minus 1 del x square. This is explicit scheme. Now here this is implicit scheme, that uin plus 1 minus uin by del T is equal to alpha un plus 1 ui plus 1 minus 2 uin plus 1 del x plus ui minus 1 n plus 1 del x square. So here you can see that the time step is forward time step. This is all our backward time step. So implicit forward time step and explicit backward time step. Now in that Crank-Nicholson method, so we have to take both and we have to add and take the average. So this is the key idea. Average of explicit and implicit methods. The Crank-Nicholson method takes the average of the explicit and implicit scheme. So now if I take the average, means if we add together and then if I take the average, so it will be uin plus 1 minus uin del T is equal to alpha half ui plus 1 n minus 2 uin plus ui minus 1 n plus un plus 1 ui plus 1 minus 2 ui n plus 1 del x square plus un plus 1 ui minus 1. Now here I am taking the del T. So here I am considering lambda is equal to alpha del T del x square. So if I take that out as a lambda, so equation become this uin plus 1 minus uin lambda by 2 ui plus 1 n minus 2 uin u plus ui minus 1 n plus un plus 1 ui plus 1 minus 2 ui n plus 1 plus ui minus 1 n plus 1. So this is actually the Crank-Nicholson methods equation. So now here if I segregate that un plus 1 term and un term, so it will be like a minus lambda by t ui minus 1 n plus 1 plus 1 minus lambda ui n plus 1 minus lambda by 2 ui plus 1 n plus 1 is equal to lambda by 2 ui minus 1 n plus 1 minus lambda uin plus lambda by 2 un I plus 1 n. So now if I write nice way, so that will means actually we are writing this. So this is nothing but the Crank-Nicholson formula. Now here I am taking as a special case. So now considering, okay, before that, so if I write in that computational tensile that will be like a, these are ui n plus 1 ui plus 1 n plus 1 ui minus 1 n plus 1, then and these are tn plus 1 means forward step, and this is the tn step. So ui minus 1n uin u1 plus n tn. So we have all these things are adding and subtraction. By this way, this formula is actually derived. Now here at Tn, known value used in the calculation. At Tn plus 1, unknown values we have to solve. And solid arrows, explicit part of the scheme. So these are explicit part, and then dash arrow, that will be implicit part of the scheme. Now, so you have to remember this, that in Crank-Nicholson tensile. Now here is the special case, so that is very important. Now if I consider lambda is equal to 1, so here if I put lambda is equal to 1, or here if I put lambda is equal to 1, what will happen? If lambda is equal to 1, so if I put that, so equation become this. And then if I simplify, so finally it will be like this. And then final equation will be ui n plus 1, 1 by 4 ui minus 1 n plus 1 plus ui plus 1 n plus 1 plus ui minus 1 n plus ui plus 1 n. So I is here 2, 3 and dot 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 n minus 1. So this is are the interior gates. So you remember, so if lambda is equal to 1, so you will get this. So here 1, 2, 3, 4, 5. So this is 5-point formula for the Crank-Nicholson method. So now here if you draw that, so if we want to calculate un plus 1, so you need that, you want to calculate this one, you need this value, this value, this value, and this value. This value divided by 4 means 1/4 of this value, 1/4 of this value, 1/4 of this value, and 1/4 of this value. Remember that. So that will be, if you remember this, so when lambda is equal to 1, so you need this 1/4 of this value, 1/4 of this value, 1/4 of this value, and 1/4 of this value. So that will be the Crank-Nicholson formula, and that can be, and if you take that interior point, so you can solve by using Gauss-Seidel method. So here notes at Tn, known values from the previous time step, notes at Tn plus 1, unknown values being computed, and solid green arrow, already computed value at the current iteration, and dashed amber arrow, value from the previous iteration, not yet updated. So now whatever this equation we are getting, so if I consider that interior point, so that interior point can be solved using Gauss-Seidel method. So here in Gauss-Seidel method, we immediately use updated value un plus 1 ui 1 minus 1, while sweeping from the left to right, accelerating convergence compared to the Jacobi iteration. So these are the theory of Crank-Nicholson method. Remember this one. So based on that we can solve many problem. So next video I'll solve one numerical problem. That's it. Thank you.